In this video, we're going to start talking about what's called simple harmonic motion, which is sort of a fancy word for or fancy phrase for a really specific type of what we call oscillatory motion. So what we're talking about here are oscillations, right? We know instinctively what oscillations are. It's some movement which is cyclical. If you've ever seen an old school clock, a grandfather clock or any sort of pendulum clock, what does it do? The pendulum goes back and forth and back and forth and back and forth. It definitely is what we call cyclical. At some point in time, it's in this far position, and then it leaves that position, but at some point later in time, it gets back into this position. You can go farther, as it swings through at the lowest point, it's at some speed, and then it slows down as it swings up. But then a little bit later, it's going to be back at that speed. And you can talk about it in terms of velocity, right? At the point at the bottom, its velocity is, if it's swinging down from the right, its velocity is to the right. At some point later, it's going to swing back and then be back to the right. And so no matter which characteristic you pick out of this thing, you're going to find some measurement, be it position, time, position, velocity, acceleration. You're going to find a certain value at some time, and then a little bit later, you're going to find the same value, and that keeps happening. So this is what we mean by an oscillation or cyclical motion. It's motion that occurs in a cycle. There are certain ways we can characterize that. If we're going to describe something with a mathematical function, which hopefully by this point in this class, if you're in my class, you've seen that that's the whole goal of physics. It's to take natural phenomena and describe them mathematically. We're probably going to have to pick out some sort of cyclical mathematical function to describe this cyclical physical motion. The one that comes to mind immediately is the trigonometric functions, right? Sines and cosines. Both are cyclical. So it's certainly possible a little bit later when we look at these equations that you should expect to see some sort of trigonometric function come in here, because if I need to describe something that's repeating, a sine function or a cosine function certainly seems like a good candidate. But first, let's get some terminology out of the way. If I measure the time it takes this pendulum, and remember, this is just an example. This is not the only type of cyclical motion. Any repeating motion is going to qualify here. But if I measure the time it takes this pendulum to get from this position back, right? We say that it has completed a cycle. If it goes all the way over here and then comes all the way back to its original position, we say that it's completed a cycle. If I take a stopwatch then and measure how long it takes to do that, I know how much time it took to complete one cycle. So I can talk about the time, should be an M, for one cycle, whatever that cycle looks like. I call this quantity the period, and the symbol is a capital T. The units are seconds, and this turns out to be a pretty important way to characterize cyclical motion. This is the time it takes to complete one cycle. You can think of it as the number of seconds per cycle. Now, cycle is not a real unit, so we don't write this as a seconds over cycles, although you could, but cycle is not a real unit in the sense that a second is a real unit. So we typically just don't write it that way. Okay, so that's the number of seconds per cycle, but that's not the only way I could characterize this motion, right? In essence, what I've done is I've picked out one cycle and measured the time. I could just have easily picked out 1 second and measured the number of cycles. You see the relationship. I picked out 1 cycle and measured how many seconds are in that cycle. I could pick out 1 second and measure how many cycles are completed within that time frame. So if I do that, I have arrived at what's called the frequency, usually symbolized with an F. This is the frequency. The units are cycles per second, but again, a cycle's not a real unit. If it helps you to write it, I don't mind if you write it, but we're probably just going to leave it off and just put the per seconds in. So sometimes you'll see it written like this. Sometimes you'll see it written like this. Most often you'll see it written like this. That stands for Hertz, after Heinrich Hertz. This is what physicists do. We find units that either we don't like or that are, painful or obnoxious to write down all the time. And then we just name them after somebody famous. In this case, I don't think the unit's that obnoxious. It's just we wanted to name something after Heinrich Hertz, so we did. So this is something you actually encounter in real life. If you look on the back of your cell phone, you're going to find a carrier frequency, probably in some prefix of hertz, megahertz maybe. But that's what that is. A hertz is a number of cycles per second. That is the frequency. I should point out, if you look in older textbooks, or if you look in advanced textbooks, like graduate level textbooks, the frequency is very often written as a Greek nu. This is a Greek n. I definitely do not write it this way because it looks way too much like a V. And most of the freshmen and most of the undergraduate textbooks have moved away from this in this day and age. But occasionally you still do encounter this. This just means frequency as well. We're going to stick with F for the frequency. So again, the period is the number of seconds per cycle. The frequency is the number of cycles per second. The similarity of the units invites us to draw a parallel between them. And then, in point of fact, there is an explicit relationship between these. The period of the motion is the inverse of the frequency, just like my units are inverses of each other, right? Seconds and 1/seconds. The period of the motion turns out to be the inverse of the frequency. That's good news, because if you have one, you automatically have the other one. You can just invert it, and then if you're given the frequency, you invert it, and you get the period. No big deal. All right, so let's talk a little bit more about frequency. What we're going to end up doing a lot is relating this frequency to what's usually called the angular frequency of the motion. And that word is a little bit unclear until you've seen the relationship. And we're going to investigate the relationship between the frequency and the angular frequency in a future video. But just to introduce you to what the symbol is, it's an omega, just like angular velocity was an omega. This is an angular frequency. And if you remember, omega as a velocity had units of radians per second. But I mentioned that a radian is not a unit in the same sense that a second is. And very often we just let the radians go. They just kind of disappear from the paper. And you're left with units of 1/seconds. Well, there are no radians in this one, or at least not until you see it explicitly. And this is the angular frequency. Its units are 1/seconds, just like the linear frequency, which we'll call hertz. So you might go, well, why do I need this, and what's the difference between the angular frequency and the linear frequency? The difference is this. The angular frequency is related to the linear frequency by a factor of 2 pi. In fact, it's 2 pi times the frequency. Where the 2 pi comes from, like I said, will be investigated in a separate video. But for our purposes here, I just want you to hang on into your mind that this frequency and this frequency are not quite the same thing, but they are certainly related. The angular frequency and what we'll call the linear frequency are just related by a multiplicative factor of 2 pi. And we will use this in just a little bit when we start to develop the equations of motion for this cyclical motion. All right, so that's a quick introduction to the terminology we're going to be using. We're going to investigate a little bit more about this in the next video and start to develop those equations of motion that will describe what these cyclical systems are doing.